All right, welcome. Today, we are cracking open one of the biggest, most important ideas in the entire world of software, object-oriented programming. This is the absolute bedrock of languages like Java, so let's jump right in and make it simple. I mean, just think about it for a second. The apps on your phone, the software you use for work, they're incredibly complicated. So how in the world do developers build these things? How do they manage millions of lines of code without the whole project just, falling apart into a complete mess? That right there is the big problem we're going to solve today. To really get why the solution is so brilliant, you have to understand the old way of doing things. Before this big shift, programming was, well, it was different. And as programs got bigger and more complex, it started to show some pretty serious cracks. So on the left, you see what we call procedural programming. The best way to think about it is like a super long, detailed recipe. It's just a list of steps, a bunch of functions that the computer follows one by one from top to bottom. The entire focus is on the actions, the procedures. But then look at the right. This is the new way, object-oriented programming, or OOP. And this just nails the difference. The focus isn't on the steps anymore. It's on the data. It's on the things themselves. Now, this wasn't just some small update. This was a whole new way of thinking about how to write software. It's a philosophy that looks at a program not as a list of commands, but as a bunch of interacting objects. And, as it turns out, that's a much more natural and powerful way to build things in the digital world. This right here, this one sentence is everything. It's the core idea. It captures the entire philosophical jump. Instead of a programmer asking, okay, what steps do I need to take? They started asking, what things am I working with? What data makes up those things? And that simple changing perspective, that's the key that unlocks everything else. So, okay, how does this actually work? It really all boils down to two key ideas, the blueprint and the thing you build from the blueprint. Let's use a really simple analogy that's going to make this all click into place. First up, you have the class, and this is important. A class is not the thing itself. It's the master plan. It's the blueprint for, say, a car. The blueprint defines all the things a car needs to have, like a color, a number of doors, an engine type, and all the things a car can do, like start, stop, accelerate. It is the design document, the master schematics. And this is the core idea in a nutshell. It's that simple. The class is the blueprint hanging on the factory wall. The object is the actual physical car that rolls off the assembly line, ready for you to drive. You just need that one blueprint, but from it, you can make thousands and thousands of unique cars. And that, of course, brings us to the object. An object is a real, live instance of a class. So if our car class is the blueprint, then a specific red four-door sedan with its own unique VIN is an object. A blue two-door convertible is another object. Each one is a totally unique thing, built from the same plan, but holding its own specific details. Okay, so this whole blueprint and object idea is great, but what makes it so incredibly powerful are four core principles. People call them the 4 pillars of OOP, and they're what give this whole approach its structure, its security, and its amazing flexibility. Let's see how they work. So here they are: encapsulation, abstraction, inheritance, and polymorphism. Now, I know these words sound kind of heavy, maybe a little academic, but trust me, with our car analogy, they're actually super intuitive. Let's tackle them one by one. Our first pillar is encapsulation. This is just the idea of bundling the car's data, like its current speed or how much fuel it has, together with the actions that change that data, like accelerate or refuel. It's all wrapped up in one package. Think of it like the hood of a car. It protects the complex engine inside. You can't just reach in and start yanking on wires. You have to use the controls the car gives you. It makes everything way more secure and predictable. And that idea of protection leads perfectly to our second pillar, abstraction. This is all about hiding the messy, complex details and only showing the user what they absolutely need to see. You don't need to understand internal combustion to drive a car, right? You just need a simple interface, the steering wheel, the pedals, the shifter. Abstraction is that dashboard. It gives you a simple way to control a very complex machine. Next, we have the incredibly efficient pillar of inheritance. This is awesome. It means you can create a brand new blueprint by just, well, inheriting everything from an existing one. So imagine you've got your standard car blueprint. Now you want to design a sports car. Instead of starting from scratch, you just inherit all the stuff from car and then add a turbo and a spoiler. It's all about reusing your work. Why reinvent the wheel? And finally, there's polymorphism. It's a big word that just means many forms. Think about the command start engine. If you do that in a gas car, it kicks off a process with spark plugs and fuel. If you do it in an electric car, it quietly activates a battery circuit. It's the exact same command, start engine, but the action it performs is totally different depending on the type of car. That is polymorphism. So, we've gone through all the theory, the blueprints, the cars. But how does this all tie back to the real world? Well, these 4 pillars are exactly what makes a language like Java so incredibly powerful and so popular for building huge, solid applications. So at the end of the day, why does this matter? Well, the advantages are massive. Because of encapsulation, your code is more secure, with its data protected. Because everything is organized into these neat little objects, it's way easier to fix and update things. And with inheritance, you're reusing code all over the place, saving a ton of time and effort. This is the solution to that chaos we talked about at the beginning. It's just a smarter, safer way to build software. And hey, this isn't just theory. You're seeing the power of OOP every single day, the critical systems that have to work in real time, complex text editors, apps like Acrobat Reader, even the way a website like Udemy can organize its courses into neat collections. All of that is built using these exact same principles. So we started this journey looking at code as just a long recipe. But now you see it's more like a factory for creating powerful, smart, interacting objects. The ideas of classes, objects, and these 4 pillars, they really are the blueprint for all modern software. So there's really only one question left to ask. Now that you understand the blueprint, what are you going to build?